equation. So today my talk will contain 4 parts. First, I will talk about the motivation of our research, and the topic is about we use the Sato-theoretical construction of the anti-self-dual multiplicarity and use it to investigate some kind of integrable reductions. So the second part is about this Sato-theoretical construction. And the third part is its integrable reductions, and the final part deals to the concluding remarks. Okay, so the motivation comes from Ward's conjecture. Yeah. Well, the anti-self-dual Mills equations it can be reduced to. I have to thank Leonard. He already talked about some backgrounds about the anti-self-dual Mills equations, so I can skip some of them. So Ward's conjecture it says that the anti-self-dual Mills equation can perhaps all integrable systems can be reduced from the anti-self-dual Mills equation or its generalizations. For example, nonlinear Schrödinger equation, KD equation, KP, Jane-Gordon, Dirac norm-dual Schrödinger, AKS, and Paddy equations. Yeah. So, but one problem is that But one problem is that the ASDYM has many different but equivalent representations. For example, it can be expressed in terms of Lex pairs, or we call it linear systems. We can assume special gauge potentials to derive some reduced integral systems, or it can be expressed in terms of Sato-Wilson equations. The Lex representation, it describes the evolution of eigenfunctions. And the Sato-Wilson equation, it describes the evolution of dressing matrix. And it has also the bilinear formulations, which describes the equations of tau function. And also matrix formulations, it can be expressed in terms of J matrix or K matrix, and as some nonlinear matrix equations. And also Twistor representations. So with those lot of different methods, they take different forms and appear to be unrated at our first glance. So there's a problem is, can these representations be unified? And here comes to our next motivation is the Sato theory. Well, Sato theory is the Sato theory of ASDYM hierarchy. It can provide a unified framework. It allows us to describe the Sato-Wilson equation, the Lex pair, which is called the linear system, or the tau function, and the ASDYM matrix formulations at the same time. So Sato theory could be a unified setting for us to investigate the Ward conjecture. Okay, and the next motivation is recently our recent work about the Gaussian matrix approach. So recently we developed the Gaussian matrix approach to investigate the integrable reduction structure of ASDYM. It turns out that several classical integral systems can be derived directly from the matrix formulations of ASDYM. So the nonlinear variables can be represented in terms of this ASDYM matrix entrance. For example, if we choose the gauge group to be ACL2, in this sense, K is a traceless matrix and J is a determinant 1 matrix. With this with these relations as our input data. So the first relation is the mirror transformation between J matrix and the K matrix. And the second equation, second relation is the T0 block for K matrix. So our starting point is just these two independent relations. However, we just from this input data, we can get a lot of integrable systems like AKN hierarchy, GI hierarchy, and so GI hierarchy is one of the three standard derivative nonlinear shading equations, and it can actually be described by the generalized derivative nonlinear shading hierarchy. And also so this is a restricted KP hierarchy. It can be derived from the squared eigenfunction symmetry of squared eigenfunction symmetry constraint of the AKN hierarchy, and also the modified KP, which is the consequence of the squared eigenfunction symmetry of chain linear hierarchy. So if gamma equal to 0, then this corresponds to GI. If gamma equal to 1, then this is chain linear. If gamma equal to 2, then this is the carbonyl. And you can see all these details in our recent research. Okay, and here comes our next motivation is the realization of cross-matrix approach, the relationship between cross-matrix approach and the Sato-Grassmann. So recently, the relationship between these two seems like different but really close related method has been discovered. It turns out that the master functions in the cross-matrix approach and the affine coordinates on the big cell of Sato-Grassmann in this Sato theory, they have some relations. They satisfy the same quadratic nonlinearity equations. So if we consider the affine coordinates of Sato-Grassmann, we can see this I and J, the index, they are all non-zero, no less than 0. But in cross-matrix, this I and J, they can be all the integers. So this is one slightly different thing. But finally, they satisfy the same quadratic nonlinear, the same equations with quadratic nonlinearity. So now, so we already have some results on. So we already have some results by using cross-matrix approach, and here is a relationship between cross-matrix approach and Sato theory. So it's very natural for us to study world conjecture in terms of Sato theory. So that's our motivation. Okay, and here are our main results. First, because because these affine coordinates, they are the index of these affine coordinates are no less than 0. So firstly, we have to extend these coordinates into the coordinates with indexed by all the integers. So we will start from this ij no less than 0, but finally we have to extend I and j belongs to all the integers. And always confused. Okay, sorry. And the second thing is that because in Sato theory, mirror shift is a very common method to generate a discrete analog. So we also want to use mirror shift to derive their discrete analog. Like we will have a continuous Sato-Wilson equation and a continuous linear system and a continuous coordinate flow. So likewise, if we can apply the mirror shift, we can get a discrete Sato-Wilson equation and a discrete linear system and a discrete coordinate flow. Because in this part, we only consider continuous case. They are partial differential equations. So if we can replace these relations with their discrete analog, it means that we can use this correspondence to derive the associated discrete analog in gradable systems. Okay. And the third result is we found the Sato-theoretical origin of the dimensional reduction constraint. Because in this part, these two relations, they are independent. So in crossing matrix approach, these relations rise naturally, but we just use it. We do not know why this relation will hold. So here we found the Sato-theoretical origin of this dimensional reduction constraint. And finally, we will use this reduction constraint to recover several classical integrable systems, and their nonlinear variables can be expressed in terms of specific radial coordinates. Okay. Okay. So the Sato-theoretical construction actually starts from Riemann-Hilbert problem. So this is the Hartree matrix or the Gould matrix. And we consider D0 and D infinity. D0 contains the point lambda equal to 0, and D infinity contains the point lambda equal to infinity. And we assume W is holomorphic in D0. W infinity is holomorphic in D infinity, and with the normalized condition W infinity equal to identity. So in this sense, W0 should have Taylor expansion, and W infinity should have Laurent expansion. So we can write down formula in this form. So in this sense, if lambda equal to infinity, then this part will disappear. So it has a normalized condition. And this is the Taylor expansion. Okay. So now we have the formula of W0 and W infinity. We can also write them in a unified expression. This is actually a piecewise function. For example, let A equal to 0, then because we set epsilon infinity equal to 1, so and infinity. Z infinity is Z larger than 0. So this is W00 lambda minus 1. And this is W1 lambda minus 1. So it corresponds with this. And finally, we can use this unified expression for us because this is more convenient. And this W matrix, after adding the time dependence, we will show they are actually the adjacent matrix, and finally they will satisfy the Sato-Wilson equation. Okay, so this is the a unified expression for W, and likewise we can write the inverse in a unified setting. So as we can see, in this part, the coefficients is W0G. Well, in this part, the coefficient is expressed in terms of Wi0. So we call W0G the zeroth column and the Wi0 the zeroth row. And finally, it can be written in this sense. But the other part remains empty. So that's why we have to introduce a generating function to fill up these empty parts. The generating function is introduced in this sense. And after introduce this generating function, it can be expanded. Sorry. It can be expanded in terms of Wij with monofolds eta minus I minus 1 and theta minus J minus 1. And because I belongs to ZA, J belongs to ZB, and A and B, they are 0, 0, 0, 0, 0, 0, infinity, infinity, 0, and infinity, infinity. So with the 4 sectors, finally, this Wij, the I and the J, they can be all the integers. And only I and J no less than 0 part, they can be identified as affine coordinates. So for example, we can write the explicitly. W infinity infinity equals to this, and we can express in terms of this. So we can see in this sense, I should no less than 0 and J should be no less than 0. And we can also prove that this relative coordinates will satisfy a recurrence relation. This recurrence relation actually generalizes Wi0 and W0J to Wij. And the generating function, the generating function, the definition encodes the information of addressing matrix, and the expansion encodes the information of this relative coordinates. So it actually establishes a direct link between the addressing matrix and the relative coordinates. Okay. So first, we will talk about the Sato-Wilson equation, which describes the evolution of addressing matrix. Well, I have to say, well, in this talk, we only consider the ASDYM hierarchy with single hierarchy time variables. Because usually for ASDYM, we should use at least 2 sequences of time variables. But in this research, for convenience, I only consider 1 single hierarchy time. But the calculation is almost the same. Okay. So we start with this partial matrix transition function, and then we introduce a differential operator. The Sato-Wilson equation is governed by this starting point. So if this equation holds, because the G can be expressed in terms of W0 and W infinity, and after calculation, we will see there will be identity. The left-hand side expands at lambda equal to 0, and the right-hand side expands at lambda equal to infinity. So finally, we will find the lambda independent function A, which is the gauge potential, and finally we will see this equation holds for all A equal to 0 or A equal to infinity. And this is the Sato-Wilson equations of the ASDYM hierarchy. So this is the evolution for addressing matrix. And as we mentioned before, the generating function establishes a link between addressing matrix and the coordinates. So it means there will be a corresponding coordinate flow. Yeah, which is given by this relation. Okay, so the calculation is direct, so I skip the calculation, just show this result. Okay, so in this from this relation, let J equal to I plus W 0 minus 1, K equal to minus W 0 0. So this setting will recover the mirror relation between J matrix and K matrix. And similarly, we can take P equal to I minus W minus 1, 0, Q equal to W minus 1, minus 1. And this will provide a mirror relation between Q matrix and P matrix. So they look very similar, and P is the inverse of J. So P can be also viewed as another form of J matrix, and Q can be viewed as another form of K matrix. So now we recall this this coordinate picture and divide it into four sectors. So we can see each starting point is exactly corresponds to each matrix. W0, 0 corresponds to K. W0 minus 1 corresponds to J. W minus 1, 0 corresponds to P. And W minus 1, minus 1 corresponds to Q. Okay, so this is about the evolution of the coordinates. Then we consider the Baker function and the evolutionary linear system. So the Baker function is actually we apply the Dirac matrix to an exponential function. So first we have to determine an exponential function. But this exponential function should not be scalar, but a matrix. So we still have to introduce a constant matrix. So finally, the exponential function is defined in these forms, and we can see this exponential function also satisfies the this vacuum function equation, vacuum equation. Yeah. Okay. So in this sense, after this definition, because we already know W satisfies the Sato-Wilson equation, E satisfies this vacuum equation, and we just substitute this into substitute this definition, and finally we will see this percent, the Baker function will satisfy the linear system. Actually, they have the same form, I think. Sorry. Yeah, the Sato-Wilson equation, if we replace W by percent, I think they are actually the same. Okay, so now we have two transition functions. The first transition function is the transition function of Dirac matrix, and the other transition function is the transition function of Baker functions, and they have this relation. Okay, then we consider the dimensional reduction constraint, and I will show where it comes from. So originally, because E, this exponential function depends on T, and G, of course, it depends on T. So usually, F should depend on P, which is time dependent. But however, if we assume F is independent of the all time hierarchy variables, it will lead to the T0 floor constraint for G, which is the T0 derivative of G is the commutator of between G and C. The proof is simple, just taking the derivative and just compute. So we take the Tn derivative of f, and use this representation to calculate, and finally we will see the inside part is partial ng minus lambda n, and with G commutator. And on the other hand, because G satisfies this vacuum equation, by iteration, we can write it as partial ng minus lambda n partial 0g. So finally, we have partial 0g equal to G's commutator. And okay, so from this relation, because G is the transition function between G is the transition function of Joyce matrix. So we substitute this definition, and we will see the Joyce matrix satisfy this dimensional constraint. Then the generating function is defined by the Joyce matrix. So and it provides the coordinates. So we find that the coordinates will also satisfy the same T0 derivative. And finally, because the ASDYM matrix variables, all of them, they are determined by this Wij. So finally, we will find this all these JK, PQ, they will satisfy the same T0 dimensional constraint. So we finally come to this. So originally, in our crossing matrix approach paper, we only use this, and here we can see why this will appear. So this dimensional reduction constraint originally appears in our previous research. At first, this is very common because this is just the natural results in the crossing matrix structure of the AKN symmetry. But we do not know why this will appear. So now we, from the perspective of Sato theory, we found this constraint is just the result of the time independence transition function of the Baker functions. Okay. Then we consider about the discrete ASDYM equations. Well, I'm a little confused, but it seems that to our best knowledge, there is little research about discrete ASDYM equations. I only found one paper, which is Benincasa and Hobart. Benincasa is Hobart's PhD student. In this paper, they employed background transformations to derive discrete Young equation, and they use it to derive some integrable systems like Shine-Gordon equations or discrete lattice modified KdV equations. So my opinion is that if we can find a discrete analog of this input data, I mean, if we can replace this mirror relation with its discrete analog, the output is these systems, they are determined by this certain matrix entrance. So it means that the output data should be the corresponding lattice equations. And I think this should be a good way for us to generate some discrete integral systems. Okay, so to begin with, we have to still assume this C has these relations. With these relations, we can calculate the shift relation for exponential function. And also for later use, we use these conventions x tilde and delta hx, which denotes the difference of x tilde. Okay, and here comes our main theory about the discrete ASDYM equation. So in the previous pages, I have showed the continuous linear system, the continuous discrete, the continuous Sato-Wilson equation, and the continuous mirror relation. So now in this theory, they are all replaced by their discrete analog. For example, if we take n equal to 0, then this is partial 0k, and it is replaced by case commutator with c. And this is partial xj multiplies j inverse. And this nebula h will, when we take h equal to h goes to 0, this would be the jx. Okay. So starting from the we still have to introduce a second mirror shift hat. So with tilde and hat, and we consider the compatibility psi tilde hat equal to psi hat tilde, and this would use this relation, and because the U can be expressed in terms of K matrix or J matrix. So there will be an equation of J and the equation of K. So this equation is the discrete Yang equation in Bianchi and Hobart. So this is Bianchi and Hobart's paper. And this equation is the middle step in calculating the discrete AKN's system by using the Kersey matrix approach in Zhao paper. So both of them can be regarded as discrete analog of ASDYM equations, I think so. Okay, and similarly, we can have a discrete analog, discrete coordinate flow of this form. This is also just by calculation by your hand, you can get this. And finally, we will have a discrete analog of the mirror relation between Q matrix and P matrix. Okay, so now we talk about the integrable reductions. Well, in this talk, for simplicity, we also we consider the very simple case, the ACL2 gauge group, and this implies the determinant of j equals to 1 and trace k equals 0, p equals to 1 and q equals 0. Because we also have to consider the discrete lattice equations, and we choose ACL2. It means if we want to use these assumptions, because n equals to 2, it means the rank of C should be 1. So C have to be diagonal 1, 0. So it has to be in this form, So in this sense, for any matrix J, K, P, Q, the T0 derivative should satisfy this relation. This cuts the diagonal part, and the off-diagonal parts remains. And also for later use, we write K and J in some simple definitions. Simple definition. Okay. So first, the first example is the positive AKN hierarchy. Recalling the LMP equation, which is the K matrix equation, and we set M equal to 1. If we take M equal to 1, then M minus 1 equal to 0. So this T0 floor are replaced by the commutator. Expanding these equations in terms of this definition, we get the equations of Q and R and U. And U Tn minus 1, Ux Tn, U can be expressed in terms of Q and R. So finally, we get a closed system of Q and R, which is the positive AKN hierarchy of the recursive operator form. And the first non-trivial member is the coupled nonlinear shading system. So this is nonlinear shading equation. And this can be also explained in Sato-theoretic. So now recall the linear system, and the telescope it in lambda equal to infinity. Then we define a new eigenfunctions in terms of this transformation, and we will see this pi matrix will become half sigma 3. Sigma 3 is diagonal 1 minus 1. And then we take n equal to 0, and it becomes this. So this part is lambda minus lambda, only diagonal part. So it corresponds to this. And this part has only off diagonal parts. So finally, it becomes the structural problem of AKN's system. And in Kake, Ikeda, Takasaki's paper, they developed this from two-component KP hierarchy and also the self-Duality Mills equation. Well, in this sense, the X-floor of the big function expressed like this. This Q matrix is sigma 3. So we can see also this is lambda minus lambda. And this part is the commutator, so only off diagonals remains. So these two relations, they are compatible. Okay. And the second example is positive GI hierarchy. Okay. So this relation comes from the T0 part, because we already take partial 0 k equal to that commutator. So the first column implies the relation of this. This Sx can be replaced by this. So finally, if we so when S is not equal to 0, we can eliminate S and finally get a clean equation between P and Q and R. So Q and R, they are components of the AKN's system. And this P introduced with Q, they compose the positive GI hierarchy. Yeah, and the first non-trivial flow is given by this equation. So this is the GI equation, the coupled GI equation. Okay, because all this calculation is already in this paper, so I will skip it quickly. Okay, so we already talked about the continuous case, and now we come to the discrete case. In the continuous case, we get the AKN's system from the continuous LMP equation. So in discrete case, we should consider this discrete LMP equation. After substituting the K matrix, it provides a system of U and Q and R. Well, on the other hand, shifting on J implies these relations. And J is determinant 1 matrix. So shifting on J do not change its determinant, do not change its determinant. So this matrix, it also has determinant 1, and we can calculate. This identity shows the difference of U can be replaced by Q and R, their combinations. So in this part, we can express them by U tilde minus U hat plus U. So finally, this part can be replaced by this. Yeah. So this is the latest AKS system. It contains Q and R, and it is closed. Yeah. So then we proceed to the latest GI system. Similarly, if we want to get the GI system, in the continuous case, we found the neural transformation between AKS and GI. So in the discrete case, it should be the same. So firstly, we rewrite the shifting relations in this form, and okay, after long calculation, we found PQR satisfy this relation. After rearranging it, we get this relation. The left-hand side is if we take h equal to 0, the continual limit, this is px, and minus r plus p square q, because h goes to 0, so this part disappears. So this is exactly the discrete analog of the continuous neural transformation between AKS and GI. Yeah, and this part is also some calculation. So we also start from the AKS, the latest AKS equation. This is the system of Q and R, and this HR can be expressed in terms of P and Q, and this KR hat can be expressed in terms of P and Q. So a direct substitution yields an equation of P and Q. And on the other hand, this relation can be written in this form. So we will see R tilde hat is isolated in this form. R tilde hat is isolated. And on the other hand, we can also write it similarly. And a direct difference between these two relations, it provides us the second equation of the GI system. So this equation, along with this equation, both of them constitutes the latest GI system. Okay. So now we can identify the AKS system and the GI system with this associated relative coordinate. So AKS, the nonlinear variables is Q and R. And they come from the K matrix. So finally, this corresponds to W00. But for GI equation, it has value from J matrix and K matrix. So it has value from W0 minus 1 and W00. So this correspondence implies that, so if we can find the explicit realization of this relative coordinates, then the continuous and the discrete AKS system and the GI system can be slowed, because this identification is very clear. So the Kersey matrix approach just exactly provides a way to achieve this. So that's why we can use cursive matrix approach to derive lot of integrable systems. So this is the main reason I think so. And also, we can get a lot of integrable systems, but I will not show details in today's talk. For example, this is the Heisenberg ferromagnet equation. We can use this S matrix. It can be expressed in terms of J matrix or Q matrix, and also some derivative nonlinear shading equations. For example, derivative nonlinear shading equation, the continuous case is very difficult. It's not so difficult to calculate, but I'm not sure if this has some discrete this has a discrete version. But I think using this method, or maybe we can get a discrete version. Yeah, and you can check these details in our paper. Okay, so finally it comes to our conclusion part. So basically, I think this research in this research, our first achievement is we extend this Wij with ij no less than 0 to ij with all integers, and the other another achievement is we find out the Sato-theoretic origin of the T0 flow, which is natural in cursive matrix approach, but not so clear, I think. And finally, we represent several integrable systems, their nonlinear variables in terms of the relative coordinates in ASDYM hierarchy. And it still remains some problems for our future discussion. For example, throughout this talk, we only choose SL2 because it's very simple and very convenient. But actually, a more natural setting is we have to choose GLN. But in this sense, we can get some multi-component integrable system. If we choose SL2, then only scalar integrable systems. And and in this talk, we only consider ASDYM hierarchy with only single time sequence. Usually, it should for ASDYM we should have at least 2 sequences. So in this research, we cannot talk about the 2 + 1 dimensional nonlinear shading equation or CBS equations, but I think the calculation is almost the same. And finally, I didn't provide too much details about cursive matrix approach because this is not the main point of today's talk. But cursive matrix approach, it provides so-called Graham type solutions, but there are also Wronskian type solutions. So I think maybe there should be some likewise. It should likewise admit some formulation in terms of this relative coordinates, which is still not clear. Okay, thank you so much.
Thank you very much.
Yes.